Good morning, everyone. Good morning to my viewers. Today we're going to analyze op-amp circuits, particularly this circuit, which is composed of 10 operational amplifiers or op-amps, and we'll try to determine the output voltage for each of these op-amps, especially the output voltage for the op-amp number 10, which is VO or V sub O. At a first glance, and to those who are not yet experienced in dealing with op-amps, this might seem complicated to analyze. It looks intimidating, but with experience and with practice, we will eventually become comfortable in solving these kinds of circuits. For a little background, let's discuss the common applications of op-amps or operational amplifiers. We have voltage follower, selective inversion circuits, a current to voltage converter, active rectifier, integrator, a whole wide variety of filters, can also be used as a voltage comparator. What is not written here is it acts as an amplifier from the word operational amplifier. So the very basic application of an op amp actually is to amplify. We have a voltage and then the output is going to be a multiple of the input voltage. It multiplies the input voltage. It means that we have a gain, voltage gain. The common is the voltage gain. It's not written here, but it is the basic application of an operational amplifier, which is it serves as an amplifier, particularly voltage amplifier. Voltage An example application is the voltage follower. Let's discuss this. Excuse. This is the symbol for the voltage amplifier. The output is there's a feedback from the output connected to the negative, the input of the amplifier. The voltage follower is also known as the buffer amplifier or unity gain amplifier. Unity gain because instead of a gain which is a multiple of the input, we have the gain is equal to 1. It is also called buffer. It serves as a buffer. It isolates. It doesn't amplify the input signal and has a voltage gain of 1. It has a very high input impedance. A popular choice in many different types of circuits that require isolation between the input and output signal. So this is what I was saying. It isolates the input and the output. That's one example of the application of an amplifier. For the voltage follower, it isolates the input from the output. This is usually the case if we have a very high input impedance. So a usual or a common characteristic of an amplifier is it has a very high input impedance. Here in the right shows that 100 ohm load is connected between two resistors 10K, which serves as the voltage divider. This will not work in real. Sometimes it will work because the load is not isolated to this resistor. So we need to make sure that the settings of the load is not affected by the input. So we add a buffer, this voltage follower circuit using an op-amp between the output and the input so that we can isolate the load from the rest of the circuit. Alright, That's it for voltage follower. Now let's discuss the characteristics of an ideal op amp. We have this symbol for the op amp, the output and the two inputs, the positive and the negative. And then usually it has two supply voltages, VCC and negative VEE, the positive and the negative voltage supply. This is how we usually connect the voltage sources. Sometimes VCC is equal to VEE. Sometimes it is just VCC and ground. Depends on the op amp configuration. Depends on the type of op amp. Ideal op amp characteristics. It has infinite bandwidth due to the ideal gain inside of the op amp. Infinite bandwidth, do we mean by the term infinite bandwidth? So it can pass, ideally it can pass all frequencies. It can operate in all the frequencies due to the ideal gain inside the op amp. So it has infinite bandwidth. Then it has infinite open loop gain A. Open loop gain, the ideal is it has infinite open loop gain. It says here open loop because in reality we have a gain of the op amp because we connect the output to the input. There's some sort of feedback between the output and the input of the op amp. And then infinite or zero common mode gain. Common mode, this is related to the terminals, input terminals 1 and 2 here. So it has infinite or zero common mode gain. The difference between the input, actually we haven't discussed it in here. The difference between 1 and 2, the voltage difference actually is 0 for an ideal op amp. It says here the input impedance of an infinite value. The input impedance is of an infinite value. Again, let's try to simplify. The output impedance is 0. So ideally for an op amp, first the input impedance is infinite. Input impedance is infinite and then the output impedance is 0. The common mode gain is 0. And when we have an infinite impedance, it means that infinite impedance, there's no current flowing. That's why I1 here is 0. Also I2 is 0 for an ideal op amp. So we always have to remember these characteristics of an ideal op amp if we try to analyze op amp circuits. So I1 equals 0, no current flowing in this terminal. I2 equals 0 also. And then the voltage difference between 1 and 2 is 0. I1 equals 0, I2 equals 0, and voltage difference is equal to 0 here. Remember that for the analysis of op amps later. We'll apply this characteristics of an ideal op amp. And then these are the formulas for calculating the gain. Op amps, as what I've mentioned earlier, they have a gain. We attain a not infinite value of the gain if we create a feedback loop between the input and the output. Here, if this is our configuration, if our input is coming from the negative terminal and the positive terminal is connected to ground, and we have two resistors, RF for the feedback resistor, and then Rin, which is connected to Vin of our source. The gain V out over Vin is equal to negative RF over Rn. This is called an inverting op amp. Inverting op amp because the input, the gain is negative, or the output is the negative of the input times the gain, which is RF, this feedback resistor, RF over Rin. So our gain depends on the values of RF and Rin. For a non-inverting op amp, our input is coming from the positive terminal, and then the negative terminal is connected. So it's the same actually. Still, our RF and Rn are connected to the negative, or in the inverting terminal. But instead of having V in here, connected to ground, and our V in is connected to the positive terminal. And the voltage gain would be 1 plus RF over Rin. Notice that it is not negative for an inverting op amp, so it's 1 plus RF over Rin. We also have a differential op amp, where for the differential op amp, we have two inputs, V1 and V2, and we have RF and Rin for both negative and the positive. Our output voltage is equal to RF over Rin times V2 over V1. Differential, from the word difference. Our input is the input difference V2 minus V1. Then we multiply by the gain RF over Rin. For the summing op amp, we have a lot of inputs, V1, V2, and V3. Then we have one feedback resistor RF, and we have series resistances R1, R2, and R3. The gain, they're all connected to the negative terminal input. The gain is equal to negative times the quantity RF. Actually, we can put RF outside since RF is common to each term. You can just factor out RF. Negative RF times V1 over R1 plus V2 over R2 plus V3 over R3. Now, if it involves capacitances and inductor, we did not show the inductor here, but if it involves capacitors, it will be a different V out already. We have a differentiator op amp and an integrator op amp, but we will not use that in our analysis with this circuit because, as we can see here, there are no capacitances. So there's no integrator op amp or differentiator op amps here. These are all inverting and non-inverting, and there might be summing or differential op amps. Differential and differentiator are different. Now let's start analyzing the circuit. First, let's start with the input because this is where the input side, because this is where the input voltages are given. We have 10 millivolts and then negative 15 millivolts. Let's start from 1 and then 2, 3, 4, 5, 6, 7, 8, 9, 10. For number 1, this is, what type of op-amp is this? The input is connected to the negative, although there are two resistors here. These are just two resistors in parallel. We just have to get the equivalent resistance here. So this is an inverting op-amp. And we should not be bothered by op-amp 4. We should not be bothered by op-amp 4 and other circuits connected to the op-amp, because we know that for an ideal op-amp, the current here is 0, right? So if the current here is 0, then basically this is just an open circuit. We can consider this an open circuit. And we can analyze op-amp 1, knowing that this is open. Also here, current is 0. No current flowing here. We can isolate this. Okay, let's start. This is op-amp 1. Op-amp 1. Okay, so let's start by analyzing op-amp 1. What was the formula in calculating? This is an inverting amplifier. So V out is negative RF over Rin. Our RF is 100K parallel to 100K, that is 50K. 100K parallel to 100K is 50K. So RF over Rin is 50K over 25K, that is 2. And negative of that, negative RF over Rin. So negative 2 times the input, which is 10. So 10 times negative 2 is negative 20 millivolts. E equals negative RF over Rin. This is an inverting amplifier. So V out is negative 2 times 10 millivolts. So V out 1 of op-amp 1 is equal to negative 20 millivolts. We have solved the output voltage of the first op-amp, which is negative 20 millivolts. Let's go to op-amp number 2. This is also a non-inverting input. Yes, because our input is coming from the positive terminal. Our input is negative 15 millivolts. And then our RF is 500K. Our Rin is 150K. So for a non-inverting amplifier, the gain is 1 plus RF over Rin. So the gain is 1 plus 500K over 150K. Times the input, negative 15 times 1 plus 500K over 150K, that is equal to negative 65 millivolts. I did not include the milli here, but the result is negative 65, so I just placed millivolts at the output. So don't be confused as long as you know that your answer is in millivolts. Or you can just indicate here. You can add millivolts if the unit prefixes confuse you. Therefore, the output of op-amp number 2 is negative 65 millivolts. For op-amp number 2, we have solved it. It's negative 65 millivolts. So don't be confused by all those things connected here. Why didn't we include this connection here? Again, this does not affect op amp number 2. Also, notice the ground connection here. So this is basically a non-inverting op amp. We know that there's no voltage difference here, and this is connected to ground. So we just no current flowing here. We can assume that this op amp does not affect op amp number 2. For the third op amp, what is this op amp? Our input is coming from the negative. Negative, there are two inputs, right? Again, this is connected to ground, but this one is connected to 10 millivolts. We have to consider the 10 millivolts and negative 15 millivolts. This is both. In op amp, we can apply the superposition where we can isolate the contribution of both inputs. Here we have 10 millivolts and negative 15 millivolts. We can first analyze the 10 millivolts, and then next is the negative 15 millivolts. We have to zero out we replace the other input by ground if we are only analyzing one input. For the non-inverting, we have 500k over 100k, right? 1 plus 500 over 100, and then our input is 10 millivolts. So V out is 10 millivolts times 500 over, what happened? Looks confusing. Yeah, this is the tricky part. This is our gain for the non-inverting, 1 plus 500 over 100. But our input voltage here is not actually 10 millivolts. We have to find what is the voltage here at the positive terminal. Notice that this is 250k and 500k, and this is connected to ground, right? If we look at the entire circuit, this is connected to ground, so we need to take voltage division. So 10 millivolts by voltage division multiplied by 500 over the total, which is 500 plus 250k. That's why we have here 10 millivolts times 500 over 500 plus 250 by voltage division, and then that is the voltage here. That voltage multiplied by the gain for the non-inverting, which is 1 plus 500 over 100, this part. The answer is 40 millivolts. This is the output voltage due to the input 10 millivolts. Now we need to find the output voltage due to this 15 millivolts. That is for the inverting. For the inverting, it is just directly, we can ignore op amp number 2 because this is I equals 0 here. For the inverting, we have negative 15 millivolts times negative RF over Rin, negative 500 over 100. So negative times negative 15 times the gain 500 over 100, this is equal to 75 millivolts, which becomes positive since our input is negative and the gain is negative. So the result is 75 millivolts. Then we add the two. By superposition, V out total is 40 plus 75 millivolts, which is 115 millivolts. Therefore, the output voltage for op amp 3 is 115 millivolts. So we have solved op amps 1 to 3. Next is 4, op amp 4. What can you see? This is, what configuration is this? This is a voltage follower, right? For a voltage follower, the output is equal to the input. So V out For op amp number 4 is just equal to the input. But what is our input? Our input is the same as the output of op amp 1. Therefore, V4 is just negative 20, because this is a buffer or voltage follower. V out equals V in equals negative 20 millivolts. We're done with 4. How about op amp 5? For op amp number 5, what is this? Notice that if you look at the negative terminal, it's connected to ground and there's feedback. Therefore, our input is coming from the positive terminal, which is equal to V out of 1, which is negative 20. And this is, you can ignore this loop here. This is I equals 0 here. Therefore, this is a non-inverting op amp with V in is equal to negative 20 millivolts. So V out is negative 20 times 1 plus 250 divided by 50 is equal to negative 120 millivolts. You can check that with your calculator. So V out for op amp 5 is negative 120 millivolts. Let's go to op amp number 6. For op amp number 6, the positive is connected to ground and the negative is connected to, we have a complicated circuit here. Our input for op amp number 6 is actually coming from the negative terminal, and we have 1, 2, and then 3. Inverting, the gain for an inverting is negative RF over Rn. So what is our RF? For this part here, our Rn is coming from op amp 3, 150K. We can consider this a summing amplifier and also inverting. V in is V out 3 from op amp 3. So we have 3 inputs. From op amp 3, and then from op amp 2, and then from op amp 5. So 1, 2, 3. How are we going to solve this? V out is equal to, I've already combined everything here. V out, the answer is 25 millivolts. How did we arrive from that answer? For op amp 3, let's check op amp 3 is 115. So this is 115 here. (115 millivolts for op amp 3. For op amp 2, negative 65. This point here. And then for op amp 5, negative 120. Negative 120. So for first op amp, let's our RF is 500. We ignore this part here. I equals 0 here. We ignore this. Here considering only this. So V out is negative 115. Negative of, since this is an inverting amplifier, so negative of 115 times 500 over 150. And then for the next, for V2, that's negative of negative 65. Negative of negative 65 times 500 over 300. And then for negative 120, so negative of negative 120 times 500 over 200k. And then calculating this total is 25 millivolts. So our output here is 25 millivolts. So don't be confused by this resistor. No current flowing here, and this is 0 volts, connected to 0 volts. You can ignore this. So basically it's just 500k as our RF. So that's it. You can, for Opamp 6, try to internalize or analyze it carefully. Our output voltage for Opamp 6 is 25 millivolts. For Opamp 7, let's go to Opamp 7. What is this? This is an inverting, right? Oh no. No, it is non-inverting because our input is coming from Opamp 4 and the negative terminal is connected to the ground. 100k parallel to 100k, that's 50k. So our RF is 50k. So V in equals V out 4, which is negative 20 millivolts from our previous calculation. So this is negative 20 millivolts. So negative 20 times 1 plus 100 parallel to 100, that's 50k divided by 10. So 5 plus 1 equals 6. 6 times negative 20 is negative 120. So the output of Opamp 7 is negative 120 millivolts. Output of Opamp 7 is negative 120 millivolts. How about for Opamp 8? We're closer to Opamp 10. This is inverting. This is an inverting Opamp. Our RF here is 1 mega ohm parallel to 500 kilo ohm. We can calculate this. You can directly calculate using the calculator. 1 over 1 meg plus 1 over 500k quantity invert. How do we find the equivalent resistance per parallel? 1 over 1 meg, or 1 times 10 to the negative 6 plus 1 over 500k, or 500k times 10 to the power 3, 500 times 10 to the power 3, and then we invert. That is our RF. It's our RF. And we have a lot of inputs also. We have to consider our input coming from Opamp 7, then our input coming from Opamp 5, and then our input coming from op amp 1, right? 71571, because we have this loop here, and then 5, how about here, and then from 6. Seven, 1, 5, 6. Why do we ignore this part here? Because this is connected here. It's basically voltage difference here is 0. This is connected to ground, so basically this is connected to ground. So we don't include it anymore. We just include this 1, 2, 3, and 4. So V out is for 7. That's, we know that this is negative 120 millivolts. Negative 120 millivolts. So since this is inverting op amp, we place negative. So negative times negative 120 times 500 parallel to 1 amp. So we just have to solve this, divided by 100k, which is our R in. For V out 1, V out 1 is negative 20 millivolts. We know that this is negative 20 millivolts. So negative of negative 20 times 500 parallel to 1 amp, and the equivalent series resistance R in is 50 plus 25, so 75k. Then for V out 5, our R in is 150k. So let's say we have 150k here, and we know that V out 5 is negative 120. Also for V6, what is V6? Is positive 25. So negative of 25, since inverting amplifier, this is an inverting amplifier. Negative of 25 times, what is the series resistance? 150k. I know we are for V6. That's 250. 250k. So the same RF for every input, but they have different R in. Then the total is 722 millivolts. For op amp 6, op amp 8, the output is positive 722 millivolts. 2 more left for op amp 9 and 10. For op amp 9, we have, this is, the positive is connected to ground, so we have an inverting amplifier. Our inputs are 1 here from op amp 6, 1 here for op amp 3. Yeah, we have 2. How about here? You know, this is connected to ground, just like how we analyzed op amp 8. But we have coming from op amp 5. 5. And I think op amp 1 is also, where is it? Oh wait, why are we not including 5 here? We are including only 3 and 6. While for Opamp 8, we included 5 and 6 for Opamp 8. For Opamp 8, we included 1, 7, 5, and 6. But here, for Opamp 9, we are excluding 5. Excuse. Because if we look at this node here, it is connected to ground. Since we are not analyzing Opamp 8, but we are analyzing Opamp 9, by looking at the circuit, Opamp 5 is connected to ground. This point here is connected to ground, so we can exclude this. So we only have 3 and 6. V out is equal to, for V3, that is 115 here, millivolts. So negative of 115 times RF, which is 700K parallel to 700K, that's 750 over 2, or 1 over 750K plus 1 over 750K, then quantity inverse, that is 750 over 2, K over 2, divided by 100 times negative 115, the output is, and then for V6, that's 25 millivolts, so negative of 25 times 750K parallel to 7, this is parallel, 700K parallel to 750K over 250K. For V3, 100K, this is the series resistance is 100K. So the result is negative 41.25 minus 37.5, so is equal to negative 468.75 millivolts for Opamp 9. So for Opamp 9, V out is negative 468.75 millivolts. Okay, 1 to go for Opamp 10. What is this amplifier? Opamp. The positive is connected to ground, so this is inverting. What are the inputs that we're going to consider? This input from Opamp 8, and then this input from Opamp 9. How about here? We go here, this is connected to ground, therefore we can ignore this op amp. So we only have 2 op amps to consider, 9 and 8. V out for 9, that's negative 468 times negative of our RF is 500 divided by 500 parallel to 500, that's 250, divided by the series resistance, which is 50K. For V out 8, R in is 100K, negative of 722, because our input here is 722, times 500 parallel to 500 divided by 100K. The total answer is 538 millivolts. So our V out for Opamp 10 is 538 millivolts. This is the final output voltage for the entire circuit. Also, we can check if our calculations or our analysis is correct by placing it in a simulation software. For example, here I have a multi-sim simulation, and I was able to verify that my answers are correct. Can't see it, sorry. But for example, for example, I have here my op amp simulation with multi-sim. You can see that the output of op amp 10 is 538 millivolts, which confirms to our simulated output, which is 538. In my simulation, I have used the ideal op amp also. For example, in op amp 8, which is 722 millivolts, we have the same result. So you can verify using a simulation software. That ends my discussion on op amp analysis. I hope you enjoyed it and you learned something. So my advice for you is don't get intimidated by seemingly complicated circuits. Instead, practice and believe in yourself and just try to practice solving and do simulations. Thank you for watching. Please like and subscribe.